Okay, welcome everyone. We're back to Math 107. We're hard to believe already on lecture 9A. Last time we were working with chapter 3, section 3, properties of rational functions. We are experts in, I'm going to call it basic polynomial functions. We're going to revisit polynomial functions in section 3.6, I believe, 3.6 and 3.7. But for the basics, we have that taken care of. But we're going to continue on with some properties of rational functions. One of the objectives that I want to make sure we're good at, because this is going to show up again and again in calculus, is that when we have a rational function of the form y equals x squared minus a squared divided by x minus a, or divided by x plus a, that we understand the graph, the domain, and the graph of this function. It's just going to keep showing up. Section 3.4 is a greater in-depth study of rational functions and inverse joint variation and inverse variation. For math, for the calculus courses that this course is preparing you for, Math 121, 131, we're going to skip that in this course because it goes in the more detail than really what you need for your calculus courses. And there's plenty of stuff already here anyway. So we actually omit section 3.4 for this course. And then you'll be happy to see that when we get to 3.5, you've already been exposed to this, sign charts. They don't really call it sign charts, but that's all section 3.5 really is. And we've been looking at it all along, so 3.5 is going to go very quickly, I think. So we want to continue on with section 3.3, and let's just back up. The very last thing that we did in lecture 8. You remember a rational function is a fraction, and what needs to be in the numerator and denominator so that we have a rational function?
A non-negative integer.
Okay. All right, we need, okay, I think you're talking to me about polynomial functions when you say non-negative integers. So we did study polynomial functions, and then how does that carry over to rational functions? What's the numerator for a rational function? What kind of function does it have to be? In the numerator and in the denominator?
Polynomial function.
Yes. In the numerator, you need a polynomial function, and in the denominator, a polynomial function. And when you have a quotient of a polynomial and a polynomial, then you have a rational function. Okay, how do you determine the domain of a rational function? The domain. Where do you look?
Into the denominator.
You're looking down in your denominator because you know that you can't have division by 0. So you're looking to see what values of x make the denominator 0. So that's where you'll find your domain. I'm just going to follow through with this example that we were working on before. So for this simple rational function, it's all values of x except for 0. Now, when you have a rational function that is reduced to lowest terms, meaning that you can't divide out common factors, whatever makes that denominator equal to 0 becomes your vertical asymptote. If it is reduced to lowest terms, no common factors, numerator and denominator, and we'll look at one shortly that's not reduced, then you find your vertical asymptotes directly from where your function is undefined. A curve will never cross through the vertical asymptote. It can actually touch the vertical asymptote if you have a piecewise defined function, but a rational function will not cross through a vertical asymptote because that's where your function is undefined. Okay? We started looking at, well, what does vertical asymptote mean? Well, by definition, it just means that as you approach the x value of your vertical asymptote a little bit bigger, these values are going to fly off to positive infinity, or a little bit smaller. Remember, we used a 0 with the little minus sign to mean just a little bit smaller. If you have a vertical asymptote, when your curve's approaching it, it's either got to go up or it's got to go down. It can't go through your vertical asymptote. So you check around each side basically to see if the sign, S-I-G-N, when you put in numbers is positive, or the sign SIGN is negative, because it's going to go to positive infinity or negative infinity. All right. Then the next thing we talked about was a horizontal asymptote. And a horizontal asymptote, we're going to go through the book and look at the official definitions. Here's y equals 0 for the horizontal asymptote. Horizontal asymptote just means as x gets really, really big or x gets really, really small, the y value starts to approach a certain number. And those are easy to check because when x is really, really big, you can just put in some little numbers like x equal to 100, x equal to 1,000, x equal to 10,000. As x gets really big, what kind of number, what kind of y value is 1 over x squared? So like 1 over a million, that's pretty small. 1/1,000,000th of something is pretty small. It's getting closer and closer to 0. And as x approaches negative infinity, you're just putting in numbers like negative 100, negative 1,000, negative 10,000 to see what kind of y value this gets very close to. If it starts to approach a certain number, then that number y equals is the horizontal asymptote. Because this says, what does y get close to? Y gets very close to 0. Y equal to 0 is your horizontal asymptote. Okay? All right. Let's see. So we had the graph of f of x equals 1 over x squared. Let's just do a quick transformation problem and see if we can sketch the graph, identify our domains, ranges, vertical and horizontal asymptotes, and keep up with the key points. Everybody ready? Answer that's yes. You're enthusiastic about doing this. All right, so what we want to do is consider the function f of x equals 2 over x minus 3 squared plus 1. Okay, f of x equals 2 over x minus 3 quantity squared plus 1. All right, and let's just kind of write out everything that we know. We're going to analyze it. What's your basic function here? 1 y equals 1 over x squared, since you got that x minus 3 quantity squared there. Okay, so we already know what the graph y equals 1 over x squared looks like. Now, what's the next thing you're going to look at? Probably that 2 multiplied times that. So you now are going to look at y equals 2 times 1 over x squared, or 2 over x squared. What is that going to do for you? What's the words?
Vertical stretch.
Vertical stretch by factor. Remember, it's factor because it's 2 times. Factoring is multiplication. Factor of 2. Vertical stretch by a factor of 2. Okay, now what's the next thing you're going to do? Add 1. So now we have y equals 2 over x squared plus 1. This will be a vertical shift up 1. Now when you shift something up 1, the asymptotes will be shifted. Everything's shifted. Okay? All right, and then the next part, y equals 2 over x minus 3 squared plus 1. What's going to happen here? Horizontal shift. Horizontal means in terms of x value, so you're going horizontally. Horizontal shift what?
Right.
Right 3. Is that good, everybody? All right. Let's see if we can sketch this. Everybody agree with the analysis of the graph? All right, so let's see if we can shift it, sketch this. Okay. Alright, so the first thing we want to do is graph y equals 1 over x squared, and we just graphed that a second ago. So we know that's a 1, 1. We know the curve comes around approaching the x-axis as x approaches infinity. And of course, as x gets real close to 0 from both sides, it approaches infinity. Okay. All right, so we have y equals 1 over x squared. Okay, now we want to do a vertical stretch by factor of 2. Vertical means y values, factor means multiply. So we're going to take our y values and multiply times 2. So my new point is going to be what? 1, 2. And negative 1, 2. And the graph is still going to approach the y-axis as x approaches 0 from both sides. And it's going to go like this. Okay, you could plot more points, but we're just getting in a good sketch. This is y equals 2 over x squared. Okay? All right, now we're going to do a shift up of 1. Y equals 2 over x squared plus 1. And what that means is it's a shift up. So what are we going to, it's up, y values. What do? Add 1 to the y values. So we're going to add 1 to the y values. Forgot to label this one. And also, keep in mind that y equal to 0 was the horizontal asymptote. So, our asymptote will also be shifted up 1. Okay, everything is shifted up 1. Is that clear? So what I'm going to do is come in and put a horizontal asymptote. Usually just use a dotted line for your asymptotes. So now y equal to 1 is my new horizontal asymptote. And now I have the point 1, 3. 1, 3. And, whoops, negative 1, 3. Still looks pretty much the same. Everything's just been shifted up here. But now it's going to approach the horizontal asymptote. Okay. Everybody good so far? And then the next little part, let's see what color I'm going to use. Black, I guess, for the grand finale. Now we're going to shift it to the right 3. And now if we're going to the right 3, my vertical asymptote also shifts over 3. So we're going to put a little dotted line right here. So x equal to 3 is the vertical asymptote. Okay, originally the asymptote was x equal to 0 for the vertical. Okay. All right, so now we're going vertically by 3. That means each x value is now going to have 3 added to it. So we'll add 3 to the x value. So we added 3 to the vertical asymptote. So now we have the point 4, 3. 4, 3. And we have the point 2, 3. And we'll just move our graph over. And it looks like this. By the way, we could do find out the y-intercept real fast. If you let x be 0, you get 2/9 plus 1. So So it's 1 2/9, which is exactly right here. Okay. All right, so here is the graph of y equals 2 over x minus 3 squared plus 1. Okay, and let's just double check the point. If you let x be 4, 4 minus 3 is 1, so 2 plus 1 is 3. Okay, are we good, everybody? Y'all are really good at transformations, so I think we're in good shape on that. Okay, let me ask you a question about this. Do I need to hold that any longer for anybody? Okay, as x approaches infinity, what does y approach? As x approaches infinity, for this curve, f of x equals 2 over x minus 3 squared plus 1. As x approaches infinity, what does the y value approach?
0.
1.
Approaches the horizontal asymptote, which is 1. We could write that as the limit as x approaches infinity of this function 2 over x minus 3 squared plus 1. And we say that equals 1, that's just notation, but it means as x approaches infinity, though this y value will approach 1. Okay? What about as x approaches 3, but a little bit bigger than 3? What does the y value approach? As x approaches 3 with a little plus. So here is 3. A little bit bigger than 3 just means a hair bigger. So as you get real close to 3, coming in from the right side, where's the y value headed? Positive infinity. Positive infinity. And we can write that as limit as x approaches 3 from the right of this function, 2 over x minus 3 squared plus 1. And we say that that approaches positive infinity. Positive infinity does not exist, however, but you write positive infinity because it gives you a good direction. Okay, everybody good? That seemed nice and easy. You'd like to have a lot of those on your test? Okay, let's go to the, let's do another example, and then we'll go to some of the examples in the book. No, actually what I wanted to talk about next, sorry about that, is how do you find, the question is, how do you find the horizontal asymptotes? Vertical asymptotes are easy. How to find vertical and horizontal asymptotes without graphing. Okay, in other words, how can we just look at the function and tell? So let's start with the vertical. I know I said that at the beginning of the tape, but let's get it in writing. We have y equals a rational function. I'm going to just write f of x over g of x. Of course, f and g are polynomials. Okay, f and g are polynomial functions. So how do we find the vertical asymptote? Who remembers what we said at the beginning of class for vertical asymptotes? You look in the denominator. The first thing is you want to, one, make sure f of x over g of x is reduced to lowest terms, meaning that you can reduce it. There's not a common factor in the numerator and denominator. Okay, so then the second thing is then you look at the denominator. The denominator, in our case, g of x, and set it equal to 0. Because if this thing is reduced to the lowest terms, wherever that denominator equals 0, then that's where your vertical asymptotes are going to be. Okay? And we're going to take some examples in just a second, and we'll talk about what they are. Okay, so horizontal, and all this is written in your book too, and we'll go back and look at it. Horizontal, when you have y equals f of x over g of x, again, f and g are polynomial functions, you have to, one, determine the degree of numerator and denominator. All right, so you have, if you're going to look for a horizontal asymptote, you got to look at the degree of the numerator and denominator. All right, and then there's two parts of that. A, if degree in denominator greater than degree in numerator. Okay, so if the denominator degree is bigger than the numerator, this is just a definition, and it's in your book, I'll show you, then y equals 0 is asymptote. Okay, if the degree of the denominator is bigger than the degree of the numerator. Okay, and B, we'll give you lots of examples in a minute. If the degrees are the same, the degrees in the numerator and the denominator are the same, then y equals the leading coefficient in the numerator over the leading coefficient in denominator is your asymptote. So if the degrees are the same, you just look at your leading coefficient. Remember, your leading coefficient is your term of highest power. So you take your leading coefficient in the numerator, divide it by your leading coefficient in your denominator, and this will be your horizontal asymptote. All right, your book will also go in oblique asymptotes. That is not a requirement here. Okay, I know the writing got close. Let's back up and tell me what you can't read. When we're looking for the horizontal asymptote, the first thing you check out is you say what the degree of the numerator is and what the degree of the denominator is. If the degree of the denominator is bigger than the degree of the numerator, then automatically y equals 0 is going to be an asymptote, because it just means you got a smaller number over a bigger number when you start squaring the denominator or cubing or raising it to a fourth or fifth or whatever. So that denominator is getting big really fast. So a small number over a big number gets close to 0. When the degrees are equal, then the rule is take the leading coefficient of the numerator and put it over the leading coefficient of the denominator, and y equals that is your horizontal asymptote. Okay? All right, so let me just give you some examples, then we'll flip through the book and make sure all this is clear. Okay, determine vertical and horizontal asymptotes. Okay, here's the first one. I'll just call it h of x. H of x equals 2x over x squared minus 4. H of x equals 2x over x squared minus 4, which I could factor the denominator to x plus 2, x minus 2. Many times completely factoring when possible makes life easy. Okay, so let's go for the vertical. Okay, by factoring completely the denominator, we see that this rational function cannot be reduced. There's no common factors. All right, so life is going to be very easy for finding the vertical asymptotes. The vertical asymptotes are x equal to what? -2 and x equal to +2. It's what makes your denominator equal 0 because your function's undefined there. Okay? Now let's look at horizontal. Horizontal. Okay, what was rule number 1 for horizontal? What's the first thing you got to look at?
The degree?
The degree. Okay, what's the degree of the numerator?
1.
1. What's the degree of the denominator?
2.
2. The degree of the denominator is bigger than the degree of the numerator. So that means the denominator is getting really big a lot faster than the numerator. So a small number over a huge denominator is getting close to what? 0. So the equation for the horizontal is y equal to 0. Okay? Questions? Next example. H of x equals 2x squared over x squared minus 4, which is equal to 2x squared over x plus 2, x minus 2. All right. I factored the denominator and I see there are no common factors to divide out. You want to make sure it's reduced to lowest terms before you start working on this. All right. It doesn't simplify. It's called a proper rational function. It doesn't have common factors. It's proper. So what is my vertical asymptotes? It's easy. What is it?
-2 and 2.
X equals -2, x equals +2. Horizontal. All right, what do you notice about the degree of the numerator and the degree of the denominator? They're the same. Second degree in the numerator, second degree in the denominator. So my crude definition on the previous page in my little pad here says, look at the coefficient in the numerator. So it's going to be y equals, the coefficient in the numerator is 2. What is the coefficient in the denominator?
2.
1. It's understood to be 1 here. Not degree, coefficient. The number in front of the x squared terms. So y equal to 2 is the horizontal asymptote. Okay? All right. Let's look at another example. H of x equals x squared minus 4 over x minus 2. H of x is equal to x squared minus 4 over x minus 2. All right, and I'm going to go ahead and factor that numerator to x plus 2, x minus 2. Okay, if we're looking for vertical and horizontal asymptotes, are we ready to go ahead and just jump right on and say x equal 2 is a vertical asymptote? No, why? Okay, the x minus 2 is a common factor. This is not a proper rational function. Whenever the degree of the numerator is actually greater than or equal to the degree of the denominator, it's not proper. And here, by factoring, we were able to simplify this down to x plus 2. All right, so let's play with this just a little bit. Let me flip the page. Okay? This is very important for your calculus class. It's just going to happen over and over when you do limits and work on some curve sketching. All right, let me rewrite it. H of x equals x squared minus 4 over x minus 2. Okay, before I go any further, tell me what the domain of this function is. The domain. Exactly. Whenever you're looking for the domain of a function, you do not go in there and simplify it and play around with it and change its appearance. You have to state what the domain of the function is as it is given. So your domain here is x is all real numbers, but x cannot equal 2. Exactly. Now, what we noticed was, in the previous page, that when we factor the numerator, this function becomes x plus 2. But I must carry the domain with it. So h of x becomes the function x plus 2, but you cannot include x equal 2 in your graph. Okay? You have to carry your domain after you simplify your function. All right, so let's just do a quick graph here. I'm first going to do it with a pencil and then go back over it. All right, whoops. Okay, this is the graph, of course, of what, everybody? Y equals x plus 2? Line.
Oh, linear. Straight.
Right, linear function. Good. Y equals 2, the slope, the intercept, the slope is 1, so you go up 1 over 1, down 1 over negative 1, and here's the graph. Up 1 over 1. Hopefully that kind of looks like a straight line here. Okay, so if I graph this, it looks like this straight line. But what did my domain say?
Not including 2.
You better leave out where x is equal to 2 because it cannot be part of this function. So where x is equal to 2, which means the x value, the y value is 4, I'm going to put a little open circle here. A little open circle. And then I'll sketch the rest of the line coming through. So the graph of h of x equals x squared minus 4 over x minus 2, even though that is a rational function, it is not going to have a vertical asymptote at x equal to 2. But the domain says x can never be 2, but this thing will simplify down to the line. So this is a rational function. It simplifies. You have to carry the domain with it. Is that good, everybody? Everybody okay? Questions? All right, let's flip through the book, and then we're going to work some exercises. I'm on page, I want to make sure we got everything covered. In section 3.3, and I'm on page 334. We talked about the domain of a rational function. We know what a rational function is. It's a polynomial divided by a polynomial. We find the domain very easily that if we look to see where that denominator is equal to 0. Look for any restrictions there. We know how to find the vertical asymptotes of a rational function. If the rational function is reduced to lowest terms, wherever that denominator is 0, those values for x will be your vertical. Find the horizontal, I've crossed out oblique because it's not an objective of Math 107. The horizontal rational function, you got to look at the degree of the numerator, degree of the denominator, once it's already reduced to lowest terms, and it's the coefficients of those. And remember, I added a number 4, limits, because we wanted to talk to you about limits. Okay, let me flip through the pages here. Just pointing out to you, whoops, on like page 337, here's this notation of limits that I've been talking to you about, just so you'll go through and read that on page 337. And there's like limit as x approaches 2 with a little plus there, and there's x approaches 2 with a little minus there. I'm just letting you know that's in your book. I didn't just get too creative here. All right, page 338, the top. Remember I told you a horizontal asymptote? It says if as x approaches negative infinity, and I need everybody to say verbally what that word is. As x approaches negative infinity, what's the other word there? Or. It's not an and situation. And means both things have to happen. This is or. As x gets really big or x gets really small. So you're looking at me backwards. X gets really big or x gets really small. Then the values, the y values, that r of x, the y values approach some number L, then the line y equal L is the horizontal asymptote. So as x gets really big or x gets really small. Horizontal. If x approaches some number C and the y value, and they did an absolute value, if the absolute value of the y function is infinity, we looked at it whether it went to positive infinity or negative infinity. Then the line x equals c is the vertical asymptote. The graph of a vertical asymptote never intersects the vertical asymptote. The graph of a rational function never intersects its vertical asymptote. Actually, intersecting meaning crossing through. Again, there are cases where you have piecewise defined functions and it can touch the vertical asymptote. It just is not going to pass through. Okay, down at the bottom of page 338, locating your vertical asymptotes. And what does it say about the rational function when you're locating your vertical asymptotes? What's those words right there?
Lowest term.
In lowest terms. Got to reduce it to lowest terms. And then it tells you it will have a vertical asymptote at x equal to r if r makes the denominator 0. X minus r is a factor in your denominator. We factored. Okay? All right. On the bottom of page 339, I've said the word proper. A rational function is proper if the degree of the numerator is less than the degree of the denominator. Okay? And whenever the degree of the denominator is bigger, y equal to 0 is going to be your horizontal asymptote. Okay? All right. Flipping on, flipping on. Okay, page 343. Page 343. Finding the horizontal asymptote. Okay, we're not worried about oblique in here. They're telling you to look at the rational function. Notice you got a polynomial in the numerator and a polynomial in the denominator. And n is the degree of the numerator, m is the degree of the denominator. Okay? When the degree of the numerator is less than the degree of the denominator, meaning the degree in the denominator is the biggest, then y equal to 0 is the horizontal asymptote. It's written right here for you. And the part of number 2 we want to look at is when the numerator and the denominator have the same degree. Numerator and denominator have the same degree. Then you look at the coefficients of the leading terms. Y equal to that is your horizontal asymptote. That's the only part of that summary you need to hang on to for this course. Everybody good? All right, let's go to the book, page 344, and let's just do a couple problems out of here pretty quickly. All right, we're on page 344, number 14. This is a piece of cake. Right here. Page 344, number 14. The instructions are, what is the domain of this rational function? Quickly. Domain.
All real numbers except for x cannot equal -3 or 4.
Perfect. All real numbers except x cannot be -3 and x can't be +4. Perfect. Everybody good? That sounded too easy, didn't it? Let's look at problem number 24. Problem number 24. Right here. What is the domain looking from the picture? What's the domain here? Domain. Are you thinking x or y for domain? X. Okay, what x values are covered here?
All except negative 2.
All except -1, I think. And that at x equals -1. Okay, so your domain is all real numbers except x cannot be equal to -1. What is the range here? What are you thinking about for range? Y values. What's your range?
All real numbers greater than 0.
All real numbers greater than 0. And if you look carefully, there's a little dotted line in red coming outside the x here. They're telling you there's a horizontal asymptote there with that little dotted line. So your range is y has to be greater than 0. Okay. What is the vertical asymptote? Vertical asymptote. Thank you. X equals, because it's a line, you have to say x equals -1. Okay, if the question is what's the vertical asymptote and you put -1, then you get minus on your test with a big old red mark. Okay, an asymptote is a line, so that is x equals -1. What is the horizontal asymptote here?
Y equals 0.
Y equals 0. Very good, very good. Okay. Next example, number 30. Number 39. Wait, is that the one I want? Number
That's what we did.
39.
No, we did 39.
Oh, we did one similar to 39. All right, let me just go back and let's just talk about number 39. 39 is x squared minus 4 over x squared.
Yeah.
Okay? Now, there's not a common factor in the numerator and in the denominator, right? All right, so let's just analyze this graph. All right, number 39. R of x equals x squared minus 4 over x squared. Okay, and we could factor x plus 2, x minus 2 over x squared. Whichever form is going to work best for us here. All right, no common factors there. What is my domain? What's my domain for this function?
All reals except for 0.
Okay, x is all reals, but x can never be equal to 0. Okay, because this is already reduced, there's no common factors in here. What is my vertical asymptote? What's my vertical asymptote? X equal to 0. All right, let's see if we can do a quick little sketch as we're here. Okay, x equal to 0 is the y-axis. X equal to 0. All right, what is my horizontal asymptote?
Okay, so it would be x equal to 1.
Not x equal to 1. Close.
Y.
Y equal 1.
equal 1.
You look at the degrees are the same. The coefficient, leading coefficient in the numerator and denominator are both 1. So y equal to 1 is going to be our horizontal asymptote. Y equal to 1. Okay. Do you know any x-intercepts? X-intercepts.
0, 1.
X-intercepts. How do you find your x-intercepts?
That y.
Set Y equal to 0.
Y equal to 0. So if we set y equal to 0, we get 0 equals x plus 2, x minus 2 over x squared. Of course, x can never be equal to 0, so we could multiply both sides by x squared, and we get 0 equals x plus 2, x minus 2. What's my x-intercepts?
Negative 2 and 2.
Negative 2 and 2. Okay. Now what do you think is going to happen? Let's do a little sign chart. Sign chart. Okay, and just let's see what's going to happen. We need to check around the zeros, and we need to check around the vertical asymptote. So I'll just do a little sign chart with a negative 2, 0, and positive 2. And we're just going to look to see are y values positive or negative, so we'll know where they are. All right? If you pick a number bigger than 2, such as 10, a number bigger than 2, such as 10, what are you going to get here? A positive, positive, positive. So you have your y values are positive greater than 0. Okay. All right, between 0 and 2, a number like 1. If I put a 1 in for x, what do we know about our function here? Is it positive or negative?
Negative.
Negative. R of x is going to be less than 0. So when we're bigger than 2, it's going to have to be approaching our y value, right? Our asymptote. And between 2 and 0, we're down here. So we already know this part's like this, coming down. Now, we know as x gets really big, it's got to approach this. The next little part we have to see, though, is does it cross the horizontal asymptote? A curve can cross its horizontal asymptote. It just can't cross its vertical asymptote. All right, let's keep going. We'll go back and see what's going to happen over here. All right, between 0 and -2, an easy point is -1. So if I put a -1 in for x, that's going to be positive. That one's going to be negative. And so we have negatives. So r of x is less than 0. So it's coming down like this. And then if we're less than -2, such as like -10, this would be a negative times a negative, which is a positive, over a positive. And we have r of x greater than 0. Okay. Now our question now becomes, we know it's approaching this horizontal asymptote. Does it always stay underneath the horizontal asymptote, or does it touch it and then come back down? All right, so hold this thought just a second as we do a little algebra. Our question is, does it ever touch the horizontal asymptote? Does r of x equal to x squared minus 4 over x squared cross the horizontal asymptote? Okay? So if it's going to cross the horizontal asymptote, what's the y value going to have to be equal to if it touches it? 1. So we'll come back and replace r of x with 1. 1 equals x squared minus 4 over x squared. Everybody clear on where this 1 is coming from? That is where the horizontal, the y value is 1. And if it's going to cross over, we're going to have to be where y is equal to 1. All right, so if we cross multiply, because x can't be equal to 0, multiply both sides by x squared, we get x squared equals x squared minus 4. If we subtract x squared from both sides, we get 0 equals minus 4. And what do you say about something like that? Impossible. It's impossible. So that means this function, our rational function, can never equal 1. Never equal 1. If it had come out to be like x equals 3, it would have meant that it would have gone up and touched the horizontal asymptote and come back down. But since we got an impossible situation, we're now ready to finish our graph. Okay? So this says the y values are bigger than 0, but we know it's got to approach this line. So we're going to curve it around like this. And over when x is less than -2, the y values are positive, and they got to approach our horizontal asymptote, so it's going to look like this. So this is the graph of r of x equals x squared minus 4 over x squared. Everybody good so far? Yes.
How are y'all getting these domains?
How did you get domains?
Yeah, like just from looking at the problem.
Right. The domain, you have to look at your rational function before you reduce it or do anything to it. And because you can't have division by 0, you just look at the denominator to see what makes it equal to 0. And if x is equal to 0, you would have division by 0. So therefore, since you can't divide by 0, x can't ever be 0.
Okay.
Got it? All right. I had one more thought. Oh, I know. The other little thing I wanted to tell you was, because we talked about it, when you go back to the problem r of x equal to x squared minus 4 over x squared is not proper. It's not proper. What do we mean when we say it's not proper?
The degree of the numerator is greater than or equal to the degree in the denominator.
Perfect. The degree of the numerator is greater than or equal to the degree of the denominator. So when you have a rational function that's not proper, you could do long division and look at what you have. Simplify by long division. X squared goes into x squared one time. And then we bring down the minus 4. and we get minus 4 over x squared. So this rational function, if you wanted to do transformations, is really the function r of x equals 1 minus 4 over x squared. So if you analyze this, it would look like your basic graph, y equals 1 over x squared. Then you would look at y equals minus 4 over x squared. With the minus 4, the y values are multiplied by negative 4, which is going to send it down. And then you would do a shift up of 1. Okay? All right. And if you wanted to do transformations, you would have had it, but we wanted you to be able to look at it with vertical and horizontal asymptotes. All right, so since it was not proper, you could do the long division there. Everybody good? Okay, what else did I want to do? Number 44, was that it? No. Number 44 was similar to 39. I think you've got homework problems. Let's just talk about it really fast. I know what it was on number 44 I wanted to get your attention on. For number 44, I would encourage you to change the order in the numerator. G of x equals 1 minus x squared. X squared minus 5x plus 6. The reason I changed the order in the numerator for number 44 is because now you see easily how to factor that. How does the numerator factor? 1 minus x times 1 plus x. All right, difference of 2 squares. I remember when I looked at it in the book, I thought, well, everybody know that commutative property of addition, you could rewrite that as 1 minus x squared and see how to factor it. Okay? All right. And then, of course, you would just factor the denominator, what's that, x minus 2 and x minus 3. All right. So now that you've got those, let's just quickly talk through it. There's no common factors in the numerator and denominator. So what is your domain here? Just say it. X can't be 2 and 3. What is the equation for your vertical asymptotes? X equals 2, x equals 3. What is the equation for your horizontal asymptote?
Y equals 1.
Not 1.
Negative 1.
Negative 1. Okay, because there's a minus there, that's like minus 1 over 1. So y equal negative 1 is your horizontal asymptote. All right, so pretend on the test you didn't have a graph and the question was this. What is the limit as x approaches infinity of 1 minus x squared over x squared minus 5x plus 6? If you had that question on the test, what would you quickly say that answer is? As x gets really, really big, you said it, say it loud.
Negative 1.
Negative 1. Remember, the definition of horizontal asymptote is as x gets really big or x gets really small, the y value approaches that. So y equal to negative 1. Or your limit's going to be negative 1. It just means that's your horizontal asymptote. Okay, what about this one? The limit as x approaches, I'm just going to put 2, and I'm going to do an absolute value here because I don't know if it's positive or negative. I'm going to do 1 minus x squared over x squared minus 5x plus 6. Okay, I'm just doing an absolute value because I don't know which direction. But you told me you had a vertical asymptote at 2. So what happens as you get real close to 2? Where's the curve headed? Infinity or negative infinity? By me doing this absolute value here, I can just put infinity. Okay? Everybody good? All right, I think we are now experts in this section. All right, we're going to skip section 3.4, although we've kind of done part of this, analyzing your graph, looking, I'm on page 346. We're skipping some of this because this goes into much more detail than what we really needed for the course, but let me just point out that you can already do a lot of this. The domain of your rational function, reducing your rational function to lowest terms, locating your x and y intercepts. We really did these things already. We don't do symmetry in this course. Vertical asymptotes, horizontal asymptotes, and then sketching your graph. So we basically did this already, but this particular section seems to get a little more in depth than what we really wanted to push you to. By the way, on page 347 at the bottom, there is a horizontal asymptote here, y equal to 0, the x-axis, and this is an example of the curve passing through the horizontal asymptote. Remember, we checked in the earlier problem to see if it crossed the horizontal asymptote. I'm sure there's some other ones in here. Yes, on page 350, I just want you to see that these things happen. 350, figure 52, these particular functions have two vertical asymptotes, and it has a horizontal asymptote. But the interesting thing about the horizontal asymptote, when y is equal to 3, this curve is passing right through the point 63. It comes slightly underneath it, but it still approaches the asymptote. Now in calculus, what's going to happen is you could use derivatives to find out how far this goes down before it curves back up to approach that asymptote. So this is an example of where it crosses the horizontal asymptote. Again, this section is much more detailed than what we need for going into the business calculus class. So we skipped that section. All right, let's look ahead, and then we're going to have to stop and start back. But now we're headed to section 3.5, and I have just simply labeled this a review section. All we're going to do is a sign chart of polynomial inequalities. I'm on page 360, section 3.5, 360. I'm labeling this review. We'll just look at a quick sign chart of polynomial and rational inequalities. This is going to be about a 5 or 10 minute exercise in the next tape. And then we're going to jump very quickly into section 3.6. You will need your book for this because this is just full of definitions, theorems, etc. Okay? All right, we're going to stop there and we'll start back shortly. All right, welcome back. We're at lecture 9B, and we're going to quickly go through section 3.5. This is really a review of sign charts for polynomial and rational expressions. This could have easily been done at the beginning of chapter 3 or in the review chapter or chapter 1. We've already been working on that. And then we're going to go into 3.6, real zeros of polynomial functions. So far, we've had just polynomial functions that had real easy zeros of the function. Integers, I think integers is about the only thing we looked at, maybe some rational zeros. But we're going to study polynomials a little further, learning how to come up with what rational zeros are when you've got more than a quadratic. I think if it wasn't already factored for us, we could use it was a quadratic and we could easily find it. So 3.6 and 3.7 is more work on polynomial functions. All right, so in section 3.5, I just called it a review and a sign chart. We're going to take a polynomial inequality, and actually in this section we're really just looking at expressions. We're not even looking at functions. Our examples are expressions. That's why I said it could be in a review chapter or chapter 1, and rational inequalities. However, the author of our textbook, and Aaron pointed out between tape 9A and 9B, that by having already studied polynomial and rational functions, that when we're looking for the inequalities, if we think in terms of a function, we're really looking at where the y value is negative for it being below the x-axis, y value is positive. So if you're working with expressions, which is what this section's on, if you're trying to think back in terms of functions, it's just where it's negative is where it's below the x-axis and positive above. But the whole thing is built on sign charts, and thought I read it, the book somewhat. Right in the middle of page 361, they really have a number line drawn here, and this is basically the way we've been doing a sign chart, but I don't know that your Arthur, the textbook, ever calls this a sign chart. Don't see it anyway. Okay, so that's what we'll be doing. This is about a 10-minute exercise. It really is going to help us in sketching polynomials. Also, in the next section, we have the intermediate value theorem, and we'll be using sign charts for that to help us figure it out. All right, so I'm just going to jump right on page 365, example number 23, because only thing we're doing is looking for where the inequality is positive and where it's negative. I'm on page 365, and the instruction says solve each inequality algebraically. Solve it algebraically. And all of the inequalities that you see in the exercises are not functions. They're just expressions. There's no y in here, no f of x. When it tells you to use your graphing utility, it's telling you to pretend that this is a f of x function, and you're looking to see maybe where the graph is below the x-axis, where it's above, etc. All right, so the whole deal is solving inequality expressions. I do want to jump back right here on page 365 at the top. Are you prepared? Notice that's a linear inequality, and I think the very first day of class we had a linear inequality. Remember, you solve it just like an equation, but when did you reverse your inequality sign? When do you reverse that inequality sign?
Change the negative.
Okay, multiply through by a negative, or what else? One other place. Multiply by a negative.
Divide.
Or multiply or divide through by a negative, or what else? There was another situation where you reverse your inequality sign.
Reciprocal.
Reciprocals. Good. If you take the reciprocal, both sides. But our exercises this time involve polynomial expressions or rational expressions. And we'll just use a little sign chart to do this. Okay, so our first problem is number 23. And we have x cubed minus 2x squared minus 3x is greater than or equal to 0. And we're just looking for all the values of x that we can substitute in here that makes this inequality greater than or equal to 0. So I think if you were just going to make a little cookbook, the first step is must have 0 on one side of inequality. Okay, must have a 0 on one side of the inequality. And in this case, it's already set up that way. If it's not, we would just subtract whatever's on one side and send it to the other side. But rule number 1, you want to have a 0. And then the second thing you want to do is factor completely. To find, I'm going to call it zeros. In other words, what makes each equation, make it become an equation equal to 0, and then we'll go to a sign chart. Okay? All right, so this one is already has 0 on one side by itself. We'll look at one in just a second that does not. And we want to see if we can completely factor this. So what would be the first thing you do to factor this inequality?
Factor out of x.
Okay, x is a common factor to all the terms, so that's x times, parentheses, x squared minus 2x minus 3. Okay. And then you notice you have a quadratic here that can be factored to what, x minus 3, x plus 1. Okay. Now here's where we've completely factored this. And we know that when x is equal to 0, or x is equal to 3, or x equals -1, this entire left side will become exactly equal to 0. And this says greater than or equal to 0, so we know all of these 3 points are a solution to this inequality. But we're also looking for the values of x that make it greater than 0. Okay, so our intervals then will be greater than 3, between 0 and 3, between -1 and 0, and less than -1. All right, so let's just plug and chug away. If you pick a number bigger than 3, such as 10, and put it in those factors, all you're looking for a sign just means is it positive or negative. So if you pick a number bigger than 3, such as 10, this factor is positive. The next factor is, say it.
Negative.
You put a 10 in for x. 10 minus 3 is
Minus 3. Positive.
positive. And put a 10 in for x here. Positive. So 3 positives. So that means that whatever this is, the inequality is positive there. Okay, let's do between 0 and 3. What's an easy number? Positive 1. So this first factor is positive. The next factor is negative. The next one is positive. So we've got positive, positive, which is negative. Does this seem easy, everybody? Yeah.
I just have a question. You said put in a number that's greater than 10?
Greater than 3.
Greater than 3, okay. And then put one in that's between 0 and 3?
Right.
Okay.
Do you know why I'm doing that?
Yeah, that's what I'm confused about. Why?
Okay, the -1, 0, and 3 is what makes this inequality totally equal to 0.
Okay.
So anytime you're on the other side of 3 bigger, this expression either will come out to be positive or negative. It can't ever be 0 again because you have already found all the zeros. So
Okay.
on each side of 0, it's either got to be bigger or smaller. Positive or negative, positive or negative. Okay, so between 0 and -1, an easy number is like a half, -1/2. So if I'm checking -1/2, this first factor is negative. What about the second factor if x is -1/2? Negative. So I've got 2 negatives, and then a -1/2 here is positive. So a negative times a negative times a positive is positive. And then a number less than -1, I would just pick something like -10. So we have negative, 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 so negative. All right, so our question is really to find all values of x that make this inequality true. Where is it greater than or equal to 0? So we'll do this in interval notation. So between -1 and 0, so in interval notation, remember use a square bracket to 0. And then the symbol we use is a little union sign, which means and also, actually it really means or. The answer is here, or the answer is over here, 3 to infinity. And any values you pick in these intervals will make this a true statement. Okay? All right. Aaron suggested that if you thought of this as the functions like we've already studied, if you think f of x equals x cubed minus 2x squared minus 3x, that this would be like a third degree polynomial functions. The ends of the graph have to go opposite directions. And there are no multiplicity in the zeros if you had that function x times x minus 3, x plus 1. Remember when you had multiplicity 2, it would touch the graph and turn around? So since all the zeros are of multiplicity 1 and it's a third degree, the ends are going to go opposite directions, and so the graph would just have to curve like this if it were the function. Okay, so 2 ways to think about it. All right, everybody good on that? Easy? You'd like a lot of these on the test. Don't count on it.
So if it was
Okay.
x squared, it'd be positive on each end.
If you have a even degree coefficient on your 0, x minus whatever, then it's going to come down and just touch it and go back, assuming that it's a positive coefficient in front of that. All right, let's look at number 53. This is a rational inequality. Rational inequality. This is, again, about a 10-minute little exercise. We're on page 365, number 53. 2x squared minus x minus 1 over x plus 4. We want to know where is this less than or equal to 0. Rational inequality. Okay, let's write it down. 2x squared minus x minus 1 over x minus 4 less than or equal to 0. All right, if you remember the little cookbook I just gave you, you always want a 0 on one side. And now let's completely factor. Numerators and denominators. Denominator's already factored. Okay, it looks like it's going to be 2x plus 1, x minus 1. I believe that's correct. Okay. All right. What is going to make this inequality exactly equal to 0 is when x is, what, a negative 1/2, and x is positive 1. If this were your rational function, these would be your x-intercepts, right? If this were a function, what makes the numerator equal to 0, there would be your x-intercepts. All right, at x equal to 4, this function is undefined. So since this says less than or equal to, there's really no way x could ever be 4 because that wouldn't be part of the domain. So we have to put like a little open circle at positive 4. I'm putting solid dots at 1 and at negative 1/2 because it says or equal to 0. But wherever the denominator is 0, I have to have an open circle there because we can't have division by 0. It's not part of the domain. Is that clear, everybody? All right, so now we're ready to pick some points. A value bigger than 4, such as 10, all we have to do is keep up with negatives. Put a 10 in this factor, positive. 10 in this factor, positive. 10 in this factor, positive. Everything's positive. So this rational expression is positive for values of x bigger than 4. Okay, between 1 and 4, easy number would be like 2. Does everybody know where those numbers are coming from? Okay, if I put a 2 in here, that's positive. 2 in x minus 1 is positive. 2 in x minus 4 is negative. So I have 2 positives and a negative, so we have a negative. Everybody good? All right. What's the easiest number in the world between 1 and negative 1/2? 0. 0 is easy. All right, so we have 1, negative 1, negative 4. So we have 2 negatives and a positive. So that's going to come out to be positive. And then a number less than negative 1/2, like negative 10. First factor is negative. Second factor is negative. Third factor is negative. So you got 3 negatives there, and it's going to be negative. Remember, division is the same thing as inverting and multiplying. So if you multiply an odd number of negatives, it's going to be negative. All right, so where is my solution? Am I using the positives or the negative for the values of x that satisfy this inequality? I'm using the negatives because it says less than or equal to 0. Where is it negative? All right, so in interval notation, we're coming from negative infinity up to negative 1/2. And I'm going to do a square bracket because the problem said or equal to 0. What's my little symbol in here? Union. And then we're going to pick up at 1. we're going to go to 4, but I have to use a parenthesis at 4. Why did I have to leave out the 4?
Because it's not equal.
Right, we can't divide by 0, undefined at 0. All right. One last problem, and then we are an expert. That's going to be problem number 49. Number 49, and I'll just write it down. 2x plus 5 over x plus 1 greater than x plus 1 over x minus 1. Okay, we're solving for all values of x that make this inequality a true statement. 2x plus 5 over x plus 1 greater than x plus 1 over x minus 1. Following my little cookbook, what's the first step? You got to get one side of this a 0. So let's just subtract this rational term, x plus 1 over x minus 1, from both sides. So we have 2x plus 5 over x plus 1 minus x plus 1 over x minus 1. Okay, remember when you're working with an inequality, you can add or subtract to both sides without changing the inequality sign. Okay, what's my next step, everybody? We're going to have to factor this so we can set up a sign chart. But I got 2 terms, so what's the next step? Common denominator. Yes. Very good. Have you been studying ahead, or are you just good? All right, what's my common denominator here, everybody?
X
X
plus
plus
1
1
times
times
X.
X minus 1.
X plus 1 times x minus 1. Very good. Okay, so the first term, we're going to have to multiply by x minus 1 over x minus 1. And the second term, we have to multiply by x plus 1 over x plus 1. All right. So x minus 1 times 2x plus 5, we need to FOIL that out. And I'm going to do it in this step right here. So we'll have 2x squared. I'll put in every little step. Plus 5x minus 2x minus 5. That's the first FOILing. X minus 1 times 2x plus 5. And then we have minus. And then when we multiply x plus 1 times x plus 1, do we get x squared plus 1? If you multiply x plus 1 times x plus 1, you get, yes, you got to FOIL it out. X squared plus 2x plus 1. I said that because that's a mistake that happens way too often. It's not x squared plus 1, you got to FOIL it. Greater than 0. Right now, let's clean it up. 2x squared minus x squared is 1x squared. 5x minus 2x is 3x. 3x minus 2x. 3x minus 2x. Sounds like plus x. Is that right?
Yep.
Thank you. Negative 5 minus 1 is minus 6. Negative 5 minus 1 is negative 6 over x plus 1, x minus 1. Okay, and now we're so happy to see that that numerator completely factors.
Can't factor it anymore.
I believe you can. Let's try. I think it factors to, let's write it again, x squared plus x minus 6 over x plus 1, x minus 1 greater than 0. I believe that factors to x plus 3, x minus 2. Correct? Over x plus 1, x minus 1. Okay? All right. I'm going to help us get going with the next step, and then we're going to move on, because I know you know what to do after that. Okay, we completely factored. Is there a question this far, anybody? You followed what we did. We had to get 0 on one side. In order to factor, we had to get a common denominator. I've now completely factored. Notice this is a strictly greater than 0. So when I set up my sign chart, I'm going to have little open circles around all the numbers because it's strictly greater than 0. So what makes each factor equal to 0 is -3, but I'm going to have an open circle because it's going to get as close to -3 as possible, but it can't equal -3. +2, open circle. -1, and a +1. Okay? And then you just continue checking your signs and getting your solution. All right? Everybody good? All right. We are ready for section 3.6. You'll need your book for sure because we got a lot of theorems and definitions in section 3.6. 3.6, we're on page 367. Page 367. We're going to learn what a remainder theorem will do for us in terms of real zeros of a polynomial function. So you want to learn what is that remainder theorem. And then we have something else called a factor theorem. So what does that factor theorem say, and what does that have to do with real zeros of a polynomial function? Another useful tool for learning, locating zeros of a polynomial function is called a rational zero theorem. So far, all the polynomials we've worked with, we could easily factor. We're going to use the rational zero theorem when we're given some polynomials and we can't factor it. We're going to look to find some real zeros of a polynomial function. What's going to normally happen is that we're going to get down to a quadratic, and we can use a quadratic formula and get to some real zeros. Solving some polynomial equations we want to look at. And then a very important theorem, intermediate value theorem. This pops up again in your calculus class, intermediate value theorem. All right. To get us started in section 3.6, let's go to Are You Prepared? Because I want to use a couple problems in the Are You Prepared to lead into the lesson. Okay, so we're on page 378. Page 378. And let's divide up. Everybody not work so hard. All right, this group over here, you three. You can be number 1. You 3 can be number 2. You 4 number 3. And I guess I'll do number 4 myself. Y'all are number 3.
Long division. Yeah.
Oh.
I know, right?
Yeah.
We have to factor the expression 6x squared plus x minus 2.
I always wanted that other one.
Started to write square root.
3x plus
-2
3x minus 2
integer.
times 2x.
Oh, you just
Hang on, I have to search for it in my pocket.
just did this the other day. What about the square root? That's the top.
Okay, I'm done.
2, 3, 4.
You know, we could be like.
Yeah, well, that over that, like, it's a fraction, it's not an energy. If it's a fraction, it's a rational number, and integers are those things.
No,
Okay, so for
the
answer,
one
you said that
I'm not
you
sure.
said that
Trick up first.
What's the long division?
Once you see it,
I'm trying.
right now.
this is 1/2
Till you see it.
4.5 used times 2.
4x to
I
the
don't know what
4th.
it is. I don't think that's square root inclusion.
Yeah, that doesn't matter.
Yeah, that's just, isn't that what you said?
No, she's saying the 1 and the 2 inside.
That matches. I thought you were talking about
I
it.
was like, no, it matters.
You were talking about
It's
that can be different.
Okay, let's see what we got here. Okay, number 1, we're looking at a set of numbers. And this is just going back to review what is an integer and what is a rational number. And I'm going to take it a step further, what is a real number. Okay, first of all, let's go back and review. What is the set of integers? Like dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Okay, set of integers. All right, so the question is, name the numbers that are integers. So you folks said -2, 0, and that looks like it. That's all your integers. Okay, integers. Okay, what is the definition of a rational number? Definition of a rational number.
A number that we can express as a fraction.
Okay, it's an integer over an integer, right? Integer divided by an integer. Of course, the denominator can't be 0. So you just said you could write it as a fraction. And what else did you say?
I was going to say about the denominator can't be 0.
Okay, so it's just an integer divided by an integer. All right, so we will mark that in green for the rational numbers. Okay, so what do you see on here that's rational numbers? 1/2,
4.5.
4.5.
Okay, 4.5 can be written as an integer over an integer, like 45 over 10. Okay, so that's a rational number.
Pi.
Pi is not a rational number. The other thing
can
about
write it as an
rational
integer.
numbers is it can be expressed as a decimal that terminates or repeats. For example, it could be written as the fraction 1/4, which is 0.25, or 1/3, which is 0.3 with the 3 repeating. Rational number, pi is not a rational number because it's a non-repeating decimal.
But I thought you could write it as an integer, as integers though.
Excuse me?
I thought you could write it as a fraction.
What fraction would that be?
It's like 720 over like 280 or something.
That might be an approximation for pi, but pi is a non-repeating, non-terminating decimal. You can we approximate like 3.14 or 3.141 or something like that, but it doesn't
I
repeat.
think it's the exact number, but I don't
Okay,
remember.
now that is not all the rational numbers. Do you see any more?
There's -2.
-2 is also a rational number because you can write that as -2 over 1. Okay, what other rational number do you see? 0 is a rational number because you can write that as 0 over any other number that's not 0, like 0 over 4. Okay? The integers are a subset of the rational numbers. All right. What about real numbers? Real numbers take in rational and integers. Okay, these are just subsets of the real numbers, but real numbers, you write them, any number you can write as a fraction, a over b, of course b not equal to 0, but you can have, it includes non-repeating decimals. Non-repeating decimals and non-terminating. Non-terminating. Okay, so real numbers also include what you already have, but now real numbers also include negative square root of 2, because square root of 2 is a number that doesn't repeat or terminate, and pi is a number that doesn't repeat or terminate. Okay, what's another real number that's not considered an integer or rational number? Square root of 3, square root of 7, square root of 5. Okay, those are also real numbers. Okay, now notice our section is locating real zeros of a polynomial function. So we might have something like minus square root of 2. What kind of number is this? Square root of minus 2. Complex. Okay, there's not a real number value that you can take the square root of negative 2. Everybody good? Questions? All right, let's go to number 2. Number 2 is just reviewing you on factoring. 6x squared plus x minus 2. How'd you factor that?
3x plus 2x minus
2x minus 1. Okay, let's double check that. 6x squared, a negative 3x, and a positive 4x when you FOIL this out, gives you a positive x, and 2 times negative 1 is negative 2. Good. All right, number 3. Did you guys do long division? All right, long division. X minus 3 into 3x to the 4th minus 5x cubed. I'm going to fill up every little placeholder, plus 0x squared plus 7x minus 4. You write your dividend in descending powers and your divisor in descending powers. Okay, x goes into 3x to the 4th, 3x cubed times. So 3x cubed times x is 3x to the 4th minus 9x cubed. What's the next step? Subtract. So don't forget to distribute your negative. And when you subtract, you will have, what, 4x cubed? Let's go ahead and bring down the rest of the dividend so we don't lose it. Right, x goes into 4x cubed, 4x squared times. So we have 4x cubed minus 12x squared. Okay. Don't forget that we are subtracting. So now we have positive 12x squared, and we'll bring down the 7x minus 4. Everybody remember doing this a long time ago? X goes into 12x squared, what, 12 times? 12x. 12x squared minus 36x. We're going to subtract. And I believe if you say, yep, 43, x minus 4, and x goes into this 43 times. We have 43x minus 129. Thank you. Then we're going to subtract. Is that right? 9, 12, yeah. So this becomes a plus, and it looks like, is this 125? Okay, so we have with a remainder of 125. Sometimes we write that as 125 over x minus 3. Okay, who remembers how to do synthetic division? Yeah, we want to do this by synthetic division, and we especially want to do it by synthetic division because we're going to be looking at the factor theorem and remainder theorem and intermediate value theorem, and synthetic division is going to be a nice little way to do this. All right, and I'm sure your book referenced you back. I think it's probably on page 53. 53. Okay, it's going to teach you how to use synthetic division, and I'm going to use the example we just did to look at synthetic division. Now, nobody's going to say you must do synthetic division or you get a 0, okay? But it's a quick and easy way for doing long division. It's a shortcut for doing long division. All right, and I'm going to show you how you do this one. Synthetic division is simply using only the coefficients. Only the coefficients, and then life is going to be nice and great. Okay, so for synthetic division, your divisor must be in the form x minus, I can't remember if your book uses a R or a C, but it's just some little letter here. We'll just do x minus r. Now, as soon as I said your divisor must be in this form, there's ways to work around to get your divisor in this form, but for this class, this is all you need it to be. Okay, x minus r. So if this had been like x plus 3 divided in this, you would write it as x minus a negative 3, if that had been a plus. Because we got to locate the r. That's going to be our divisor. So we write 3. And now we list just the coefficients of our dividend in descending powers. And you got to have a place for each term with the x in it. So you'll have 3, negative 5, 0, 7, negative 4. So we're dividing by the 3 because it has to be in the form x minus the r. This is the r part. And then you just list the coefficients in your dividend. 3, negative 5, 0, 7, negative 4. It's very important every position is covered. All right? Now life is great, so just watch this. You always bring the first coefficient down. And then we just say 3 times 3 is 9, and you put it right here. And then you just add. 9 and negative 5 is 4. And then we go 4 times 3 and put a 12 here. And we add. 12 times 3 is 36. And we add. 43 times 3, 129. And we add. Okay? Now, the last position is always the remainder. And your quotient is always 1 degree less than your dividend. So then all you have to do is come back in here and put 3x cubed plus 4x squared plus 12x plus 43, and there's your remainder of 125. So synthetic division is very fast, and it's just a way of working with the coefficients. All right? Everybody good? All right, you practice those because life is great when you use them. All right, so now where is all this leading to and why is it important? Well, the first thing I want to do is jump on what is called the remainder theorem. The remainder theorem. I'm on page 368. 368. Let f be a polynomial function if f of x is divided by x minus c. So if you do the division of this function by x minus c, then the remainder that you get when you did the long division or the synthetic division, the remainder that you get is going to be the same thing as evaluating the function at that C. All right, remainder theorem says that if you take a polynomial function and you divide by x minus c, then basically whatever your remainder is, that's the same thing as evaluating the function at that c. All right, so I'm going to go right back to this problem. The same problem that we had here. I'm going to illustrate the remainder theorem. All right, so we're going to pretend that our function, I'll just call it p of x, our polynomial function is 3x to the fourth minus 5x cubed plus 7x minus 4. All right, that's the dividend that we just had, correct? All right, now suppose your instruction says find p of 3. Well, normally what you would do is you'd come over here and say, okay, p of 3 is 3 times 3 to the fourth minus 5 times 3 cubed plus 7 times 3 minus 4. And then you would just plug away on your calculator. Okay? And you should do that just to verify. Well, if you plug and chug this away on your calculator, the value of this function at 3 is going to be 125. If you put this in your calculator, well, we should do it just so that you're a believer. Okay, so it's going to be 3 times 3 raised to the fourth minus 5 times 3 raised to the third plus 7 times 3 minus 4. Okay, I just punched all that in the calculator. Equals, and there's my, can you see it, 125? 125. Okay, so the nice thing about the remainder theorem is it says, suppose you don't have a calculator real handy, and you're trying to evaluate a function at a number, you can do a little synthetic division real fast in about 3 seconds, and whatever that remainder is, that is the value of the function there. Does that make sense? All right, so let's read the words again to the book and make sure it's very clear. If we have a polynomial function, if we divide that function by x minus c, and remember c will be your divisor for your synthetic division, then the remainder, when you did the synthetic division, is the same as the value of the function at that c. How's that? Pretty neat? Pretty neat. Okay, now let's go to the factor theorem at the bottom. If we have a polynomial function, then x minus c is going to be a factor of that polynomial. So we're going to be able to find a linear factor of that polynomial function if and only if f of c equals 0. All right, let's back up. Remember when you said a function equal to 0, you found the x-intercepts? And if you had an x-intercept, then x minus that number was a factor. All right, so what this is going to do for you is combine the remainder theorem for you. If you're trying to find a factor, then if you just did your little synthetic division and got a remainder of 0, you're going to immediately know that x minus c is a factor. All right, let's take a simple example. Now because, oh, by the way, the problem that we just did, because the remainder is not 0, then we know that x minus 3 was not a factor of that polynomial. All right, so let's take an easy problem that we already know the answer to. Given f of x equals, what, x squared minus x minus 6, use the remainder and factor theorems to determine if x minus 3 is a factor of f of x? And we already know the answer is yes, but we're going to illustrate the theorems, okay? So f of x is equal to x squared minus x minus 6. What we're trying to do is come up with more interesting polynomial functions and learn to factor it, okay? And we're going to use the remainder and factor theorem. All right, so we're going to have to start out with the remainder theorem, which says, all right, well, let's find the value of this function at 3 using synthetic division. That's because I don't want to do long division. So let's divide 3 into, remember the coefficients, 1x squared minus 1x minus 6. I'm going to do the remainder theorem first. All right, everybody knows where the 3, the 1, negative 1, and negative 6 come from? So I bring down the 1. 1 times 3 is 3, add. 2 times 3 is 6, add. The last position is 0. Okay. Now, jumping on the factor theorem, it says that x minus c is a factor if and only if the value of the function at c is 0. The remainder theorem said when you divided by x minus c, then the remainder is f of c. Okay, putting it all together. The remainder theorem, since this is 0, it says that f at 3 equals 0. That's the remainder theorem, right? The remainder is the value of the function at 3. Now the factor theorem says, if and only if f of 3 equals 0, then x minus 3 is a factor. Okay, so the question was, is this a factor? Yes, it is. We know it is because f of 3 is 0. We know f of 3 is 0 quickly because it was the remainder when we did the long division. All right, that was just a shortcut, easy way to find f of 3. Everybody good?
Did we have to put on the remainder theorem? Did you have to use the synthetic? Couldn't you just plug in the 3?
Well, if you're doing remainder theorem, it's talking about division.
Mm-hmm. Oh.
That when you divide, the remainder that you get for division is the value of the function there.
Okay.
But if you weren't told anything, of course, f of 3, you just plug in a 3 and get your y value. But it's trying to show you a quick and easy way to evaluate functions. If I have to evaluate functions sometime and I don't have my calculator and the numbers look really bad, I just jump on the remainder theorem and I have it. All right, so let's go to the exercises in the book. And we're not going to finish this section today, but at least we can do one of these problems. Okay, I'm on page 379. Page 379. Okay, and let's pick an even one. Let's try number 16. I have no clue what the answer is. Number 16 on page 379. We're supposed to use the factor theorem to determine if x minus the c is a factor of this function. And if it is, we're supposed to write it in factored form. Okay? All right, so number 16, I have no clue what the answer is, so don't let me make an arithmetic mistake. All right, so number 16, we have f of x equals 2x to the 6th minus 18x to the 4th plus x squared minus 9. And we want to know, is x minus our c, or in this case, x plus 3. Is x plus 3 a factor? Okay? Since my c is a minus 3, it would mean is x plus 3 a factor? All right, so the thing we want to do is jump on the remainder theorem with synthetic division and see if that remainder is 0. So my divisor is minus 3. And you tell me the numbers to go across for synthetic division. What is it? 2?
Minus 18.
Is the next
0.
one minus 18?
0.
0. All right, be sure you star that in your notes so you don't miss it. You've got to have a placeholder. Okay, So we got 2x to the 6th, 0x to the 5th, and now we got a
Negative
minus
18.
18x to the 4th. What's next?
0.
0x, 1x squared,
And negative
0x minus 9. Okay? 6, 5, 4, 3, 2, 1, 0. Got to have all the coefficients for all the positions. All right, here we go. Don't let me do any arithmetic mistakes. Bring the 2 down. 2 times negative 3 is negative 6. Add. Negative 6 times negative 3 is positive 18. Add. 0 times negative 3 is 0. Add. 0 times negative 3 is 0. Add. 1 times negative 3 is negative 3. Add. Negative 3 times negative 3 is positive 9. Add. 0. Wasn't that easy? I did that fast to motivate you. Were you motivated? Okay. All right. I have a remainder of 0 here. What does the remainder theorem now tell me?
X
That's
plus
what
3
3 is.
The value of the function at negative 3,
is 0.
0. If I had plugged in negative 3 and raised it to the 6, which would be kind of hard for me to do without my calculator, and multiplied it times 2, minus 18 times negative 3 to the 4th, and all that. If I add that up with negative 3's in for x, that whole expression will come out to be 0. All right, now that we know the value of the function at negative 3 is 0, would we say x plus 3 is a factor? Yes. So by the factor theorem, since f at minus 3 equals 0, then x minus a minus 3 or x plus 3 is a factor. Okay, so we found a factor. All right, now I want to go a step further. I don't know how many minutes I have left. 3. Okay, we have 3 minutes left. I'm going to go one step further. So, and we'll pick up on this next time. If I needed to factor this function, I am now down to this much. F of x equals x plus 3 times what?
2x to the 5th.
2x to the 5th minus 6x to the 4, 3, 2,
X
plus x
minus
minus 3. So what we're going to learn to do is keep breaking this down further and further to its factorization. Okay? So you can look forward to this next time. Make it a great day, everybody.